Welcome back to the deep dive. If 2024 was the year of the prototype, well, 2025 has definitely been the year the large language model agent went fully operational.
Oh, absolutely. We're seeing this rapid, really widespread adoption.
Yeah, sophisticated, multi-step agentic workflows across the enterprise world.
And not just chatbots, right? We're talking complex financial analysis, optimizing entire global supply chains.
And the payoff they're promising is immense. You keep seeing these industry surveys pointing to automation gains, promising, what, a 20 to 30% cost savings?
It's a huge economic driver. Very compelling.
Super compelling. But, as we often see, the speed of adoption, it can really outpace our ability to safely control what we've built.
That's the core issue.
When that kind of money is on the table, what are the unseen risks? What's lurking beneath the surface here?
Well, the big risk is systemic instability. And it's coming from insufficient evaluation, especially once these things are live in production environments. We're hitting major technical, operational, even organizational roadblocks.
Yeah.
The traditional LLM testing. It focuses on narrow, controlled benchmarks.
Right, lab conditions almost.
Exactly. But in the real world, these agents, they make decisions through pathways that are, well, emergent, not standardized. They don't follow a neat little flow chart.
And that makes oversight difficult.
Difficult.
Yeah.
Almost impossible.
Yeah.
Especially when you think about auditing regulatory bodies. If failures aren't caught, or worse, if they start compounding across multiple agents.
We get systemic errors.
Systemic errors, financial losses, massive legal liability, current evaluation methods, even the good ones, they're just dangerously insufficient for this new reality.
Because they miss the cascade effect.
They miss the cascade, the emergent behaviors, the stuff that happens when agents interact with messy, real-world data and complex logistics.
Okay, that brings us right to our mission today then. We're diving into a framework specifically designed to bridge this exact gap. It's called AgentCompass, and it's positioned as this comprehensive solution for robust post-deployment monitoring and debugging of these autonomous workflows.
Yeah.
So what makes it fundamentally different? We've talked about benchmarks like GAIA for general reasoning or Trail for task completion. How is this a step beyond those?
It's a fascinating shift, really, in scope. GAIA, Trail, they're essential, don't get me wrong. They establish baseline technical metrics, accuracy on static data,
Okay.
but they neglect the crucial stress tests, like human-centered context, tricky edge cases, even the sort of emotional intelligence needed for high-stakes interaction.
Things that matter hugely in production.
Critically. And the problem in production often isn't that an agent fails all the time. It's that when it fails, the error or the bias, it compounds in really unpredictable ways, especially with multiple agents interacting.
Right. Okay, so here's where AgentCompass gets really interesting from what I read. It stops treating deployment like a lab test. Instead, it models the reasoning process of an expert human debugger. It analyzes the raw, unstructured trace data, the agent's full action history, its internal thoughts.
Which lets you look at long-term systemic health, not just a single snapshot score. It's longitudinal.
So how does it achieve that human-like rigor? Because asking an LLM one giant diagnostic question, that doesn't usually work well, does it?
No, it's notoriously unreliable for complex tasks.
Okay.
The task is just too vast. So they implemented a really clever core analytical technique. A recursive plan and execute reasoning cycle.
Plan and execute. Okay, break that down.
So instead of one massive prompt, the diagnostic task is decomposed. First, there's a planning phase. The LLM generates a structured strategy. For example, it might say, okay, first I'll identify all tool invocation failures, then I'll assess the agent's attempt to self-correct afterwards.
So it makes a plan first.
Makes a clear plan. Only after that plan is generated does the execution phase run, and it performs the analysis precisely following that specific directive.
So it forces a methodical, step-by-step approach.
Exactly.
Yeah.
Like a good developer following a strict debug protocol, it significantly improves the consistency, the reliability of the analysis.
I like that focus on methodical process, and that structured approach seems to carry right through their whole operation, with this multi-stage analytical pipeline.
That's right.
Like an assembly line, taking that huge, messy execution trace and transforming it into something actionable, a strategic summary a developer can actually use.
Yeah.
So let's walk through those 4 stages. They seem to get progressively more abstract, more strategic.
They do.
Stage 1 sounds pretty straightforward. Error identification and categorization. The system scans the trace, finds discrete errors, and classifies them using a formal hierarchical error taxonomy. We definitely need to circle back to why that taxonomy is so important.
Absolutely key.
Second stage, thematic error clustering. So this is where individual, maybe low-level errors get grouped together.
Right. Grouped into semantically coherent clusters. This is how you reveal systemic issues, maybe causal chains, that you'd completely miss if you just looked at isolated error flags.
Because one single error might seem trivial.
Exactly. An isolated tool failure might seem minor. But if it happens 50 times a day and it's always linked to the same underlying prompt strategy, that's a critical system flaw.
Got it. Okay, stage 3.
Stage 3 is quantitative quality scoring. So, moving beyond just describing errors, it assesses performance across predefined, objective dimensions.
Like what kind of dimensions?
Things like factual grounding, is the agent making stuff up, adherence to safety guidelines, efficiency of plan execution, did it take a sensible path?
Okay, so you get actual scores
Yeah.
and the final stage.
Stage 4, synthesis and strategic summarization. This pulls everything together, the categorized errors, the systemic clusters from stage 2, the objective scores from stage 3,
Into one report.
into one highly actionable summary. And crucially, it provides an aggregate quality score and a recommended priority level for human intervention.
So it tells the engineer, here's the problem, here's how bad we think it is, and here's how urgently you should probably look at it. The who, what, where, and how urgent.
Precisely. And that error taxonomy we mentioned, that's the foundation making this whole pipeline genuinely developer-centric.
How so?
It's derived from concepts in Trail, but it's expanded and designed, so the error category maps directly to the type of intervention needed. It helps you understand what kind of fix to apply.
Okay, let's get into those categories. There are 5 high-level ones.
5 high-level ones, yeah. The first is thinking and response issues. This covers core reasoning failures, hallucinations, flawed decision-making, maybe misinterpreting instructions.
So if you see that, you know you need to tweak the prompt or the agent's reasoning logic.
Exactly. Second category, safety and security risks. This flags harmful behaviors. Leakage of PII, personally identifiable information,
Critical.
or generating biased content, harmful stuff. Very important.
Okay, and the other 3?
Third is tool and system failures. These are more external issues. An API call failing, maybe hitting rate limits, timeouts.
Usually an infrastructure fix, maybe.
Often, yeah. Fourth is workflow and task gaps. This is where the agent kind of loses the plot, experiences goal drift, loses conversational context mid-task.
That sounds like an orchestration logic problem.
Usually requires refining that orchestration, yes. And finally, there's a category that's really key to the AgentCompass insight. Reflection gaps.
Reflection gaps, what does that mean?
This is a meta-level failure. It identifies when an agent fails to show evidence of reasoning before taking an action. Or, and this is crucial, when it fails to correct itself, even after explicitly receiving an error message.
Wow, so it's not just what it did wrong, but that it failed to think about what it did wrong.
Precisely. Identifying a reflection gap means you've found a fundamental cognitive flaw in the agent's design or architecture, not just a simple execution error.
That focus on cognitive flaws, not just technical bugs, brings up longevity. Production agents must hit similar weird edge cases over and over.
Honestly.
If we spot a systemic workflow gap, we need to fix it once, right?
Yeah.
Not debug the same symptom 1,000 times. How does AgentCompass stop engineers reliving Groundhog Day? How does it learn?
Great question. That's where they introduce knowledge persistence for continual learning. It's built on the assumption that systemic errors will recur.
Okay.
And it's facilitated by a dual memory system.
Dual memory, like short-term and long-term.
Sort of, yeah.
Yeah.
The first door is episodic memory. Think of this as short-term. It captures context and findings for one specific trace execution you're looking at right now. Helps with stateful analysis of the current debug session.
Okay.
The second is semantic memory. This is the durable long-term store. It holds generalized, abstracted error patterns and diagnostic best practices learned across hundreds, maybe thousands of traces.
So it remembers past problems.
It remembers patterns of problems and effective ways to diagnose them. It helps the system refine its own diagnostic heuristics over time. It gets smarter about debugging.
Ah, I see. So when a new trace comes in, the system checks its semantic memory, finds relevant past issues, and injects that historical context into the LLM prompts for the new analysis.
That's right. It primes the debugger LLM with the system's past experiences, its past mistakes.
That's really smart. It essentially builds institutional knowledge directly into the diagnostic tool itself.
It does. And that memory system feeds directly into how the framework handles issues that appear across multiple executions. That's the trace-level issue clustering.
Okay, you mentioned thematic error clustering earlier as stage 2 of the pipeline. Is this related? How does trace-level clustering work, technically?
It builds on that idea. To
Huh.
make the clustering meaningful across many traces, they use some advanced techniques.
The source material mentions using the HDBS scan algorithm on error embeddings. That sounds pretty technical. What are error embeddings? And why use fancy math instead of just like keyword matching?
Good question. An error embedding isn't as scary as it sounds. It's basically just a complex mathematical representation, a vector of the failure narrative.
The story of the failure.
Yeah, the specific actions, the internal thoughts of the agent, the tool outputs, everything that defines that specific failure instance. You can't use simple keyword rules because real-world failures are nuanced.
How so?
Well, two agents might fail a financial task for different surface reasons, but the underlying semantic meaning of their failure, say, a fundamental flaw in how they handle uncertain data, might be identical. Embeddings capture that deeper meaning.
Okay. An HDBS scan.
HEB scan is a powerful clustering algorithm that's good at finding clusters based on density in that embedding space. It doesn't need you to tell it how many clusters to look for.
So it can discover new recurring types of problems automatically?
Exactly. It finds these recurring constellations of semantically similar failures without engineers having to manually define every possible failure pattern beforehand.
And this clustering turns abstract patterns into what? Something engineers can track.
Into quantifiable tickets, essentially. Things that engineering teams can actually track, prioritize, and manage in their regular agile development cycle. It takes the abstract pain and makes it concrete, actionable work.
Very cool. And that rigor seems to have paid off during validation. They tested AgentCompass on real-world deployments.
They did, on partner deployments, and also against the public trail benchmark, which itself includes complex traces from datasets like GAIA and SDB bench.
And the quantitative results. Did it perform well?
Very well. The results show methodological superiority. AgentCompass achieves state-of-the-art performance on trail, especially excelling in precision,
Precision-like.
like superior localization accuracy. It was significantly better at pinpointing the exact moment or span in that long trace where the error actually occurred.
Which is critical for debugging. You need to know where it broke.
Absolutely. And then there's the real acid test, the strict joint score.
What does that measure?
It requires this system to correctly identify both the error location and the error category simultaneously. Get either wrong, and you get 0 points for that instance.
Tough metric.
Very tough. And AgentCompass set a new high-water mark for this joint score across both GAIA and SWE bench datasets within Trail. It shows that rigorous plan and execute cycle really works integrating precision and accurate categorization.
Okay, solid quantitative results. But you mentioned something else, a qualitative finding that sounded even more compelling.
Yes. For me, this was the crucial finding. The AgentCompass system identified valid errors that human annotators had missed in the original benchmark datasets.
Wait, it found real errors the humans miss.
Yes. This is the moment where the automated rigor, driven by that detailed taxonomy and methodical process, actually surpassed human review capabilities, at least within the constraints of benchmark annotation.
Okay, we need specifics here. Give us one of those examples where it found something the humans overlooked.
Certainly. In one case from the source, a human annotator had flagged an error simply as instruction non-compliance. The agent had uploaded a file that exceeded an explicitly stated size constraint.
Okay, sounds like a minor procedural slip-up.
That's how the human saw it. But AgentCompass, using its richer taxonomy, reclassified it. It flagged it with much higher severity as a safety and security risk data exposure.
Hold on. How is exceeding a file size limit a data exposure risk?
Because the investigation revealed that the file size constraint wasn't arbitrary. It was an explicit negative constraint designed specifically to prevent the agent from handling potentially massive, untracked data dumps. These large dumps could easily contain PII or other sensitive corporate information that shouldn't be processed by that particular workflow.
So violating that specific rule wasn't just about file size. It was about potentially mishandling sensitive data.
Exactly. AgentCompass recognized that violating a negative constraint about data handling isn't just a formatting error. It's a potential security failure, a compliance risk. That insight completely changes the severity and the required response.
That would definitely change the priority of the fixed ticket. Instantly. What was the other key example? Something about a cognitive flaw.
Right, that was the detection of a reflection gap, specifically identifying a lack of self-correction. The system spotted instances where a subagent would get an explicit error back from a tool like an API timing out.
Okay, happens all the time.
But instead of pausing, processing the error, and maybe trying something different, the agent would immediately retry the exact same failed action with the exact same
Or
parameters,
just banging its head against the wall.
repeatedly, sometimes recursively, leading to this cascade of identical, predictable failures. A simple monitoring tool might just log 50 API tool failure events.
Right.
AgentCompass diagnosed the meta-level reasoning flaw. The agent failed to pause, reflect on the error message, and adjust its plan. It lacks self-correction. It even found subtle tool selection errors happening way back in the agent's initial planning phase that only later led to downstream problems like hallucinations.
So it's doing root cause analysis that traces back to the thinking process itself.
That's the goal. Deeper root cause diagnosis.
Okay, so pulling this all together, what does this mean for you, the listener, who might be managing or building these kinds of systems? It seems like Agent Compass is genuinely trying to bridge that huge gap.
Right, the gap between narrow academic benchmarks and the messy, high-stakes reality of enterprise deployment.
It looks like a structured, actionable path towards more trustworthy, more robust, production-grade agents.
And critically, it provides a more profound, actionable diagnosis.
Mm-hmm.
The framework can even generate prescriptive fix recipes for developers,
Like suggesting specific code changes.
or recommending concrete steps, like adjust tool invocation parameters for API X, or refine the agent's context window handling and the orchestration logic. But here's maybe the most surprising and profound finding from the validation.
Okay.
AgentCompass's overall quality scores. They only had a moderate correlation, around 0.4, with the scores assigned by the human annotators.
Wait, only moderate correlation. Wouldn't you want a high correlation? Doesn't that suggest it's not aligning with human judgment about what's a quality issue?
Normally, yes, you'd expect a high correlation to mean it's capturing human intuition well. But in this specific context, the researchers argue, and I think compellingly, that this moderate correlation is actually a desirable finding,
How could that be desirable?
because it signals that the human baseline, which was likely constrained by time and a less granular error taxonomy during the benchmark creation, was actually insufficient. The AgentCompass system, with its detailed taxonomy and rigorous process, was capturing a richer, more complete spectrum of errors and risks,
Especially things humans might overlook.
especially in areas like subtle security risks and those cognitive failure modes, the reflection gaps, things humans, reviewing quickly, might have missed or underestimated. So the moderate correlation isn't showing the system is wrong. It's showing it's more rigorous and comprehensive in its risk assessment than the human baseline it was compared against.
Wow. Okay, that reframing where finding errors humans missed is actually proof of the system's value. That's pretty profound. It really suggests our standards for evaluating AI need to evolve rapidly.
That's the critical takeaway, I think. Our
Yeah.
intuition needs to catch up with the complexity.
So to wrap this up then, we talked about the system flagging these reflection gaps moments where an agent acts without evidence of reasoning or fails to self-correct after a clear mistake. If even sophisticated AI agents are struggling with this kind of basic introspection, this learning from their own actions, what future challenges does that point to? What should developers be prioritizing to ensure these complex, autonomous workflows don't just execute commands efficiently, but can actually reason reliably when faced with the unpredictable real world?
That really is the multi-million-dollar question, isn't it?
It seems like the question facing every organization betting big on these autonomous systems right now.